This is Unit 4 Practice Exam Version B, Solutions. Question 1, we have a system. This is a linear equation, but this is a nonlinear. So the two options to solve a system of nonlinear equations, remember, is either using the substitution or the elimination method. Elimination method works great, but only if your variables are like terms. None of these variables are like terms. So we're going to have to use a substitution method. So I'm going to take this top equation, add the x over. This is going to become y equals x minus 3. So then I can take this x minus 3 and substitute it in for that y. So then the bottom equation becomes x squared plus x minus 3 squared equals 9. And then expand x minus 3 squared is x squared minus 6x plus 9. And then combine some like terms there. And then factor. And the solutions for x are x equals 0 and 3. So when x equals 0, we need to solve for y. So we use this equation here. So when x equals 0, y then equals, instead of x minus 3, I'm going to replace that x with 0. So this is 0 minus 3, which means y equals negative 3. So one of the solutions is when x equals 0, y equals negative 3. Now for the other value of x, 3, do the same thing. Now when x is equal to 3, we're going to say y is equal to 3 subtract 3, which means that y equals 0. So that solution is when x equals 3, y equals 0. Question 2, we're solving a system of 3 equations, 3 variables. So step 1 is to choose 2 of the equations and eliminate one of the variables. So I can see here that in the top 2 equations, I have negative y and positive y. So if I just take these top 2 equations here, and eliminate the y variable, I get 3x plus 9z equals 0. So that's step 1. Step 2 is to do the same thing with 2 other equations, but you have to eliminate the same variable. So since I eliminated y in step 1, I got to do that again in step 2. So I'm going to take these bottom 2 equations and multiply the top equation, or sorry, multiply this equation by negative 4, so I can get a negative 4y and a positive 4. So that middle equation would be negative 8x minus 4y minus 16z equals negative 8. I multiplied everything by negative 4. Bottom equation stays the same. So when I do elimination method there, the y is going to cancel. We get negative 6x minus 18z equals 0. Now for step 2, you are going to combine the results from step 1 and 2. So this is 3x plus 9z, and then negative 6x minus 18z. So now we have a system of equations where y is gone. We still have x and z. So now we need to solve for either x or for z. I'm going to eliminate x, which means I have to multiply this top equation by 2. So that one becomes 6x plus 18z equals 0, and the bottom equation stayed the same. So if you notice and remember, 0 equal to 0 means that there are infinitely many solutions to this system of equations. So when that happens, you have to set up a parameter and solve for a solution in terms of that parameter. So we're going to let z equal our parameter t. And then rather than jumping all the way back to the beginning, we go back to this third step here. We know that z is equal to t, so then we can solve for x. So if I take that equation, 3x plus 9z, now remember I can replace z with t, so 3x plus 9t is equal to 0. So then we can solve for x by subtracting 9t and then dividing by 3. So x is equal to 3t. So we have two of the variables. We have x and we have z. So now we need to solve for y. We do that by going to one of the original equations. I'm going to take that middle equation, 2 times x, which is negative 3t, plus y, plus 4z. Remember, z is equal to t. That's equal to 2. So this equation here is just this middle equation, original equation, replacing x with negative 3t and z with t. And now we can simplify. So y is equal to 2t plus 2. So our solution in the form x, y, z now is x is negative 3t, y is 2t plus 2, and z is t. Okay, so question 3, we're solving using an augmented matrix. And then we perform row operations to get this into row echelon form, which is 1, 0, 0. That's our first task. 1, 0, 0. This should be a 1. That should be a 0. So we're pretty much there. This needs to be a 0. This one already is. So just need to multiply by negative 1 here and add that to row 3. So negative 1 times row 1, add to row 3. We're going to make a new row 3. So that makes 1 times negative 1 is negative 1 plus 1 is 0. Negative 2 times negative 1 is 2. 2 plus 1 is 3. 1 times negative 1 is negative 1 plus 3 is 2. And 1 times negative 1 is negative 1 plus 8 is 7. So we have 1, 0, 0. If this wasn't a 1, if it was any other number, we would need to make that a 1 by multiplying this number by the reciprocal fraction. But since it's already 1, now we can focus on making this equal to 0. So if I multiply the middle row by negative 3, that's going to put a negative 3 here, which when added to 3 is going to be 0. So that's my row operation. Negative 3 times row 2, add that to row 3. It's going to become a new row 3. So 0 times negative 3 plus 0 is still 0. 1 times negative 3 is negative 3 plus 3 is 0. 2 times negative 3 is negative 6 plus 2 is negative 4. And 5 times negative 3 is negative 15 plus 7 is negative 8. And technically it's not in row echelon form, but we can still solve now. It's far enough along where we know that negative 4z equals negative 8, which means that z is equal to 2. So then we use that middle row to represent the equation y plus 2z, which remember z now is 2. 2 times 2 is 4. If you subtract 4 from 5, we get y equals 1. And then that top row represents the equation x minus 2 times y, which in this case y is 1, plus z, which is 2. So negative 2 plus 2 is 0, so x equals 1. So the solution is x equals 1, y equals 1, and z equals 2. Okay, part A here. When you're multiplying two matrices, first thing to check is if the multiplication is possible. So A times B means you have a 3 by 3 multiplied by a 2 by 3. So that's not possible. For part B, we have a 2 by 3 and a 3 by 3. So that one is. Let's go ahead and do that. So this entry is combining that row with that column. So we have 2 plus 2, it's 4, plus 0, so 4. This entry comes from combining that row with that column, so multiplying negative 2 times 2, that's negative 4. Negative 2 times 1 is negative 2, so negative 4, negative 2, that's negative 6. And another negative 2 makes negative 8. This entry is a combination of that row with column 2. So we have 1 times 1, that's 1, times or plus negative 2. So 1 plus negative 2 is negative 1, plus 0. We have negative 1. This entry is this bottom row with the middle column. So we have a negative 2 and a positive 2, which makes 0. And then 1 times 1 is 1. 0 plus 1 is 1. And then finally, this entry is a combination of row 1 with column 3. So 5 plus 8 is 13, plus 0 is 13. And here we have negative 10 plus negative 8, that's negative 18, plus 0 is negative 18. For part C, we have 2 times B minus 3 times C. And the only way you can add matrices if both matrices are the exact same dimension. So this is 2 by 3 and 2 by 3. So then the scalar multiplication just means every entry gets multiplied by, in this case, 2. And on the other matrix, everything's multiplied by 3. And then we subtract terms that are in the same spot. So like 2 subtract 18, it's negative 16. 4 minus 6 is negative 2. 0 minus negative 6, positive 6. Negative 4 minus 12. Negative 16, negative 4 minus 0 is negative 4. And 9 minus, or 2 rather, 2 minus negative 9 is 11. Solve the system using an inverse matrix means we need to create a matrix equation. And solve for this matrix xy, because that's going to tell us the value of x and the value of y. Now this matrix is being multiplied by this matrix. So in order to get this matrix by itself, we have to cancel this matrix. The only way that's done is if we can multiply it with its inverse. So if we consider this to be matrix A, then the inverse of A is 1 over that product, which is 6, minus this product, which is -1. And then remember, these two terms change places. And these two terms change sign, so that becomes a +1, that becomes a -1. So there's the inverse. So if I was to take this matrix and multiply it here, then they would essentially cancel each other out, leaving xy all by itself. But since this is an equation, if you multiply by the inverse here, you have to multiply by the inverse, by this same inverse right here. So it's going to be this times that. And I'm going to leave the 1/7 out. So I'm going to multiply the two matrices together first and then multiply the 1/7 at the very end. So this entry combines the top row with column 1, so that's +2 added to 12, which is 14. And then here we have +1 added to -36, so that's -35. So then I take the 1/7 and multiply it to that matrix. So then the xy matrix is equal to that result to -5, which means the solutions are x equals 2 and y equals -5. For part B, we do a similar process. We have to set up a matrix equation. Now, where part B is quite a bit more challenging is in order to get this matrix XYZ isolated, we'd have to figure out the inverse of this and then multiply. Now, the inverse of a 3 by 3 is very challenging to find, so that's why it's been given to us right here. This is the inverse of that. So all that we need to do, if we were to multiply this to that, cancels out, which means we also need to multiply this matrix to that matrix. So that's what we need to show. Is this matrix multiplied by the matrix 8, 6, 14. So this entry is combining that row to that column. So we're going to have -24, +72, and it's going to be 42. So you add -24 to 72 to 42. That makes 90. This entry is that row to that column, so 13 times 8, that's 104, and then -60 and -14. So we have 104 plus -60 plus -14, and that's 30. And this entry is row 3 with that column, so 8 and 8, that's 64, minus 12, minus 28, and that's 24. So now we take that 1/18 and multiply it into this matrix. "90 divides by 18 evenly. but 30 does not, so that's going to be 5/3, and neither does 24. That's going to be 4/3. So then our solution is x equals 5, y equals 5/3, and z equals 4/3. For question 6, remember Cramer's rule involves determinants. When you have two variables and two equations, you need three determinants. Determinant D is a determinant from the coefficients. So this determinant of a 2 by 2, remember, is this product. Always start with that one. So 3 times 12 is 36 minus this other product, which is 35. The next determinant, remember, follow the subscript. X means that the x column, the coefficients of the x column are going to be replaced with those two values. And find the determinant. So negative 7 times 12 is negative 84. And then 5 times 7 is 35. That's negative 119. And finally, this last determinant, if you follow the subscript, y means that these coefficients in the y column are going to be replaced with negative 7 and 5. The x column is going to be the same as it was originally. So this determinant is going to be 3 times 5, which is 15, minus negative 7 times 5, which is negative 35. That equals 50. So then, according to Cramer's rule, the value of x is dividing those two determinants, d sub x divided by d, and then the value of y is dividing these two determinants, d sub y divided by d. So the solution is negative 119, comma 50. For part B, we're going to do Cramer's rule again. Simplified version though, because we only need to solve for the z variable and not all three of them. So for Cramer's rule, z is equal to determinant d sub z divided by the determinant d. So the determinant d is just going to be the coefficients. Now to find the determinant of a 3 by 3, I'm going to use the method, one of the methods shown in class, which was copying those first two columns over here to the right side of this matrix, and then multiplying these diagonals. So always start from the top left down to the bottom right. So 4 times 1 times 8 is 32. Negative 2 times 0 times 2 is 0. And 3 times negative 6 times 7 is negative 126. Now we multiplied all three of these diagonals going from the bottom left to the top right. So 2 times 1 times 3 is 6, 7 times 0 times 4 is 0, and 8 times negative 6 times negative 2 is 96. Now, these numbers add, remember, and these numbers subtract. So 32 plus 0 plus negative 126, then we subtract 6, subtract 0, and subtract 96. So 32 minus 126, that's negative 94, minus 6 minus 96. And that's negative 196. So we'll repeat this process for d sub z. So the subscript means the z column is going to have the values here after the equal sign, 6, negative 2, and 24. Then we're going to copy those first two columns again. So from the top left to the bottom right, 4 times 1 times 24 is 96. Here we have negative 2 times negative 2 times 2, which is 8. And here we have 6 times negative 6 times 7, which is negative 252. Now from the bottom left to the top right diagonals, 2 times 1 times 6 is 12. 7 times negative 2 times 4 is negative 56. And then 24 times negative 6 times negative 2 is 288. So those numbers I have written in red, those add. And then the numbers I have written in blue subtract. So then 96 plus 8 minus 252. Those numbers, those first three at least, combine to negative 148 minus 12 plus 56 minus 288. Combining all of those makes negative 392. Well, then we have the determinant d sub z was negative 392. Determinant d was negative 196. So dividing those two, we get z is equal to 2. For partial fractions, we learned a couple of different variations depending on the denominator. In this case, we have repeated linear terms there. So we're still going to have two partial fractions, but since they're repeated and they're repeated twice, first time you write the factor, the second time you write the factor. In this case, is the second power. Now, when we multiply the whole equation here, we're going to multiply this by the lowest common denominator, which is x plus 3 squared. When that multiplies over here, the denominators, x plus 3 squared, cancel out, so you're just left with 7x plus 14. When this multiplies here, x plus 3 cancels with one of these x plus 3's, so then a multiplies the other x plus 3. Now when this x plus 3 squared multiplies to this partial fraction, the whole x plus 3 squared cancels out, leaving just b. So we have one equation to solve for two unknowns. So at this point, the process I described in class was choosing a convenient value. So if I wanted to solve for b, I'd have to cancel a, meaning that I could make this term turn into 0 by letting x equal negative 3. So if we let x equal negative 3, then here we get negative 21 plus 14, which is negative 7. Here, negative 3 plus 3 is 0, so a disappears, leaving just b. So b equals negative 7. Now, in order to solve for a, we have to have b turn into a value, not a variable. And we already know the value of b, so for the second step, I'm going to let b equal negative 7. But we also have to have x turn into something. Now I don't want to let x equal -3 again because that's going to make a disappear, and I want to solve for a. So I'm just going to let x equal some random value, like x equals 0. So I'm plugging in x equals 0 and b equals -7. So if x equals 0, I get 0 plus 14, which is 14. Here, 0 plus 3 is 3. 3 times a is 3a, and then plus b turns into plus -7. If you add 7 to 14, you get 21. So then divide by 3, and a equals 7. So the partial fractions are +7 over x plus 3, and then a -7 over x plus 3 squared. To find the first 4 terms of the sequence depends, the way that you do it really depends on whether you have an explicit formula or a recursive formula. There's some similarities there. With an explicit formula like this, you just plug in 1 for n for the first term and the second term and so on. So the first term, you plug a 1 in for n, 2 to the first power is 2, 2 divided by 2 is 1. The second term, plug in a 2 for the n, 2 squared is 4, 2 divided by 4 is 1/2. Third term, 2 cubed is 8, 2 divided by 8 is 1/4, and finally the fourth term, 2 to the fourth power is 16, 2 divided by 16 is 1/8. So this sequence would be 1, 1/2, 1/4, 1/8. Those are the first 4 terms. With a recursive formula, remember at least the first term is always given. So we know the first term is -3. Now, the second term for when n is 2, if you plug in a 2 for n here, that just means we're going to get the second term, which is what we want here. We're going to get 2 minus 1. So a sub 1 just means refer back to the first term, which is -3, and then subtract -2. It's -5. For the third term, a sub 3, plug in a 3 for n. Here just means a sub 3, which is the term we're looking for. Here, 3 minus 1 means a sub 2. So this term turns into a sub 2, which is -5, minus 2, which is -7. Then here, a sub 4 means 4 minus 1, a sub 3, which we just found to be -7, and then subtract 2 to get -9. So when we need to write an explicit formula for the nth term, it depends on whether the series, or the sequence rather, is arithmetic or geometric. So for this one, -4 to 2 to 8 to 14, the pattern here is adding 6 to go from term to term. So this one's arithmetic, and the common difference is 6. So the formula for the explicit formula for the nth term of an arithmetic sequence was first term plus n minus 1 times the common difference. The first term is -4. Common difference is 6. If we distribute that 6 and then combine like terms, we get 6n minus 10. Now, if you recall from the discussion we had in class regarding this, if it's an arithmetic sequence, the explicit formula is just a linear function, mx plus b, y equals mx plus b, where m, the slope, is just the common difference, and b, -10, would be like a term in front of the first term, the 0 term. So if this pattern continued not only to the right but to the left, then there would be a -10 here, which is where that value comes from. For part B, 2 to 4/3 to 8/9 to 16/27. So it looks like we're multiplying by 2/3. 2 times 2/3 is 4/3. 4/3 times 2/3 is 8/9. So this is geometric, because we're multiplying by the same value. And the common ratio is what you're multiplying by in this case is 2/3. Now on the formula sheet, the explicit formula for the nth term of a geometric sequence is first term times r to the power of n minus 1. So the first term is 2, common ratio is 2/3 to the power of n minus 1. Okay, for part A, we have information here that the sequence is arithmetic, so between the 6th term and the 14th term. So the 6th term is 12, and then we add some common difference over and over again up to the 14th term, which turns out to be 28. And it's important that they told us this is arithmetic. It was like I said in problem number 9, an arithmetic sequence can be modeled pretty much using a linear function. And the common difference is just like the slope. So the way this kind of a problem was presented in class is we look at this much like we do functions, linear functions, where the x column is n, that's the spot that the term is in. So the 6th spot was a 12 and the 14th spot was a 28. So the slope is the difference in y values divided by the difference in x values. So the common difference d is 2. So the explicit formula is the common difference 2 multiplied by n plus some value here. And we can use the given information that the 6th term, where n is equal to 6, is equal to 12. So a sub n would equal 12. So then that unknown starting value there is just 0. So the explicit formula is just 2n. So then for the first term, which is what they want us to find, a sub 1, we just need to multiply, plug in a 1 for n. 1 times 2 is 2, so a sub 1 is equal to 2. For part B, I just want to continue this out to the 9th term, so we have to figure out the pattern, if it's arithmetic or geometric. Now we could just figure out the pattern and then get the 5th term, the 6th term, the 7th term, the 8th term, and then write the 9th term, which really wouldn't be too hard considering it's only the 9th term. But if they wanted us to say like the 15th or the 25th term, it might be easier to have a formula for this. So this is geometric, -2 to 2/3 to -2/9 to positive 2/27. It looks like the geometric common ratio is r equals -1/3. So then the explicit formula would be -2 times -1/3 to the power of n minus 1. So then the 9th term would just be plugging in 9 for n. 9 minus 1 is 8. So we need to figure out what -1/3 is to the 8th power is. And it's 1 over 6,561. Then multiply that by -2. And the 9th term is -2 over 6,561. All right, for number 11, we're doing partial sums, and then for part E, we're going to do an infinite sum. For partial sum, there were two different formulas. One's for an arithmetic series, the other one's for a geometric. So we got to figure out if it's an arithmetic or a geometric. For this one, 17 to 24 to 31 to 38, looks like we're adding the same number every time. And that number is 7. So this is arithmetic, and the pattern is adding 7. So the common difference is 7. So the partial sum formula for an arithmetic sequence, or an arithmetic series rather, is n divided by 2 multiplied by the first term, 17, times the last term, in this case 185. What we don't know is how many terms there are in between to go from 38 to 185, because we have to know how many terms we're adding together. So we need to create an explicit formula for this sequence. The explicit formula is the first term times n minus 1 times the common difference, 7. So it's 7n plus 10. Now, we know the term itself is 185. That goes in place of a sub n. What we don't know is the n value. Is this the 10th term or the 50th term? So we don't know the n value there, but we know that the a sub n is 185. So we can take this explicit formula and solve for n. So 175 divided by 7 is 25. What that means is this is the 25th term. So from 17 all the way to 185, there are 25 terms. So that goes in for n now. First term of that series that we're adding is 17. The last term is 185. And 17 plus 185 is 202. So 25 halves times 202 is 2,525. This is sigma notation. We have a partial sum from 1 to 17, so we're only adding 17 terms. We have to decide is this a partial sum of an arithmetic or a geometric sequence. The nth term formula given here is that of an arithmetic sequence because it is in linear form. So we can use the same formula from part A, half of the number of terms, and then the first term plus the last term. Now the number of terms is 17. The first term, if we plug in a 1 for n, is 8. The 17th term, if we plug in a 17, 17 times 2 is 34, plus 6 is 40. So the sum is half of 17, and then we have 8 plus 40. So 17 halves multiplied by 48. And that is 408. For part C, we have, again, a partial sum. And is it geometric or arithmetic? So it's from 2 to 6 to 18 to 54, all the way out to here. It looks like the pattern is multiplying by 3. So this is geometric with a common ratio of 3. The partial sum of a geometric series is first term times 1 minus r to the power of n divided by 1 minus r. So we know the first term is 2 and the common ratio is 3, but what we don't know is what term 118,098 is. So what we need is the explicit formula. For a geometric sequence, the explicit formula is first term times the common ratio to the power of n minus 1. Now, we don't know the n value for this term, so we can use this formula, plug in this value for a sub n to solve for n. So 118,098 is equal to 2 times 3 to the power of n minus 1. So this is an exponential equation to solve. So in order to solve an exponential equation, we have to cancel the base using logarithms. So first step is to divide by 2. So that's 59,049. Now we can use a logarithm base 3. So n minus 1 is equal to the log base 3 of 59,049. And if we add 1, we have n equals log base 3, 59,049 plus 1. So this is definitely something that you would do on a calculator. So log base 3 of 59,049 is 10. 10 plus 1 is 11. So this is the 11th term in this series. So we have first term is 2 times 1 minus 3 to the 11th power divided by 1 minus 3. And again, this is something you would do on a calculator. So from that we get 177,146. For part D, this is a partial sum because it's from 1 to 7, and then this is the explicit formula of a geometric sequence. So again, we're going to use the same formula as from part C, the partial sum of a geometric sequence. So we need first term, 1 minus r to the power of n divided by 1 minus r. So here, the first term is 3. If we plug in a 1 for j, 1 minus 1 is 0, 1 half to the 0 power is 1. 1 times 3 is 3. The term in the parentheses there, that is the common ratio. And then the number of terms we're adding is 7. So first term is 3 times 1 minus 1 half to the 7th power divided by 1 minus 1 half. And again, this would be something you do on a calculator. And this turns out to be 5.953.125. Or if you want to keep it as a fraction, 381 over 64. For part E, this is an infinite sum. And remember the two criteria. One, this series has to be geometric, which it is because this is an exponential. And then the common ratio has to be between -1 and 1, which 2/3 is. So the common ratio is 2/3. The first term is 2. So this infinite sum of a geometric series is first term over 1 minus r, which is 6. Now, expanding a binomial from section 7.3. First thing I'd recommend doing is figuring out the coefficients of each of the terms. So the two ways you can find the coefficients of each term. One of them is using Pascal's triangle. If it's raised to the 4th power, then you need 5 rows. or you can use the binomial theorem. So the first one would be 4 choose 0, and then 4 choose 1, 4 choose 2, 4 choose 3, and 4 choose 4. So that's 1. This one would be 4. And then finding the values of each of these isn't necessarily hard to do by hand, but it's just much quicker if you're using the features on the calculator that were shown in class. So 4 choose 2 is 6, 4 choose 3 is 4, and 4 choose 4 is 1. So either way, you get the same values. These are the coefficients of each term. So for the first term, we're going to use that coefficient, 1, which we don't really need because 1 times anything doesn't change the value. And then we're going to take the first term here and raise it to that power. So it's going to be 3x raised to the 4th power. The next term has a coefficient of 4. And then now we're going to include both of these terms, 3x and 2y. 3x is going to be raised to the 3rd power, and 2y is going to be raised to the 1st power. Next term is going to have a coefficient of 6. And then we're going to have 3x raised to the 2nd power and 2y raised to the 2nd power. Next term has a coefficient of 4. 3x is raised to the 1st power this time, and 2y is raised to the 3rd power. And finally, the coefficient of the final term is 1, which we don't really need to write, and then we only need the last term, 2y, raised to the 4th power. So starting here back at the beginning, 3x raised to the 4th power. 3 to the 4th power is 81. X to the 4th power is x to the 4th. Here we have 3x raised to the 3rd power, so that's 27x cubed times 2y times 4. So we need to multiply 4 times 27 times 2. And that's 216 x to the 3rd, y to the 1st power. The next one's going to be 3x raised to the 2nd power, which is 9x squared. 2y to the 2nd power is 4y squared. And then multiply that by 6. So now we need to do 6 times 9 times 4. So that would be 216 also. X squared times y squared. For this term here, we're going to have 3x to the 1st power, and then 2y raised to the 3rd power is 8y cubed. And that's multiplied by 4. So then 4 times 3 times 8 would be 96. X times y to the 3rd. And that final term, 2y raised to the 4th power, is 16y to the 4th.